All right. So it says a baseball on the moon and an identical baseball on the Earth are thrown vertically up with the same velocity of 16 meters per second. What is the difference in the maximum height the balls reach on the moon compared to the Earth? The gravity on the moon is 1/6 that of Earth. Okay, so first step, we got to draw a picture. Here's Earth. I mean, it's pretty spot on, don't you think? So there's Earth. Here's our baseball. On Earth. Here's a person throwing it up in the air. It has an initial velocity (16 meters per 1 second). Okay? So that's the initial velocity of 16 meters per second. And we have a very similar situation on the moon. There's some craters on the moon. Okay, same thing though. We have a baseball. It too is going up at the same initial velocity. Over here on Earth, the acceleration due to gravity is 9.8 meters per second. Now the gravity on, and we'll call this G Earth, that's a little E there. Actually, I'm just going to call it G. And the gravity on the moon is equal to 9.8 divided by 6 meters per second squared. All right. So I'm just going to do that on the calculator real quick. I've got 9.8. I was having some fun drawing the pictures. 9.8 divided by 6, 1.633. So it's 1.63 meters per second squared. All right. So then the ball reaches a maximum height here on Earth. I don't understand why that does that. It's a little frustrating. At the maximum height, think of the ball. Think of the rockets when we launched the rockets. When the rockets reached up to the was somebody knocking on my door or the door next door? Is it my door? When the rockets reached the maximum height, what did they do just before they turned around and came down? They stopped. So what's the velocity of this baseball when it's at the maximum height? 0. Yeah. So my final velocity in both cases is going to be 0, right? So over here, my final velocity on Earth would be 0. Ugh, I don't like how that looks. So my final velocity, and it's not V naught, my final velocity would be 0 meters per second. Same thing over here, my final velocity would be 0 meters per second. Okay? But what I really need to know is the maximum height. So I'm just trying to double check and make sure. So what do I know? I know two velocities, right? And I know an acceleration, and I need to find the maximum height. Well, look in your free fall equations and see if there's one that'll help you with that. There's one there. You just got to look for it. By the way, how would I label maximum height? Well, the maximum height is the displacement or the distance. So you could, what we really need to do is figure out what delta y is. That's what we're trying to solve for. What is this thing? So look in your free fall equations and find the equation that has all those things. Raise your hand when you find it. Do you guys see this one? V squared equals V naught squared equals 2, whoops, not equals. Minus 2 G delta y. Did you guys find that one? Okay. Now this one's a little weird because we're going to run into a little bit of a math problem, sort of, but not really. Let's just plug it in. So now this is the formula that we're using. Let me do Earth. I'll do Earth way over here. So for Earth, I've got a final velocity of 0 meters per second is equal to the initial, and that's squared, by the way. Yeah. Is also equal to 16 meters. Actually, you know what I'm going to do before I do all this math, because it's a lot easier if I do it this way. This is a little easier. What's the final velocity for both of these? It's going to be 0, right? So I'm going to make one equation and plug the numbers in. So this becomes 0. Well, let me just do this. I'll do it this way originally. 0, and then I've got 16 meters, 16 meters per second squared minus 2. Then the acceleration due to gravity is 9.8 meters per second squared. Oops, forgot to write that down. Okay. And that's going to equal delta y. Okay. So then I got to do the math on that. So this one is going to be 16 squared. Let me pull up my calculator. 16 squared. $256. So over here I've got 0 is equal to 256. Now remember, you're going to have meters squared over seconds squared now, because you're squaring the meters and the seconds too. Minus 16.9, I think is what it'll be. 9.8 times 2. Yeah, or 19.6. I always get it backwards. So negative 19.6 meters per second squared times delta y. Now I'm going to take this term, the 256, and subtract it from both sides. So I get 256 meters squared all over seconds squared is equal to negative 19.6. Ugh, that's not good. Forgot to write my 0.6. It's important. 0.6 meters squared equals delta y. Now, to solve for delta y, I'm going to have to divide both sides by the negative 19.6 meters per seconds. I'm going to try to get my seconds in there. No, it's not going to work. We'll do seconds squared like this. Okay? And so then when I do that on both sides, I got to divide the same thing down here, negative 19.6 meters per second squared. I'm going to end up with, let me just close this off so we don't get confused. 256 divided by 19.6. So the negatives cancel, and I get 256 divided by 19.6. And it's about 13, right? So we'll say that delta y is about 13 meters. Okay. Actually, let me look at that calculator. I may have rounded that not properly. Let me do that again. 256 divided by 19.6. Actually, we should probably make that 13.1. Let's do that. Are we done yet? No, we got to do the exact same thing. So this is the distance the ball goes on Earth, right? Now we got to find the distance it goes on the moon because it wants to know the difference between the two. So I've got to find Earth. So this is Earth's. That's how high the ball goes on Earth. And I got to find the moon. Now the moon, and then I got to find the difference between the two of them. So for the moon, and I'm going to simplify this a little bit. On the moon, you can actually, you don't realize what I'm doing here, but I'm actually finding the final position, which is delta y, is equal to negative the square root, or not the square of the initial velocity over 2 times g, but in this case we'll do g moon. That is very frustrating. So I'm going to say delta y is equal to, well, what's the initial velocity? Well, they both had the initial velocity of 16 meters per second, but when you square it, it becomes negative 256 meters squared per second squared, right? And then on the bottom, I've just got to multiply the 1.6 times 1.63 times 2, right? So if I go and I grab my calculator and I type in, and it was like a lot of threes. It was like 1.63 repeating times 2. I get we'll make it 3.27. How's that? So over here, this whole thing is going to be divided by, it'll be negative because it's going down 3.27 meters per second squared. And so what happens is this second squared cancels with this second squared. One of these meters cancels with this meter, and so then I just got to plug in my calculator. 256 divided by 3.27, and I end up with like 78.3 roughly. So that is for the moon. Right. All right, we're almost done. Oh, we got to go. So then you subtract both those. So what's 78.3 minus 13.1? Well, it's about 65, and we did some rounding, so it's 65.2. I think the answer is actually 65.3 in your books. So we did some rounding. That's it. And that one took longer than we thought, huh?